So we're going to talk about the history of microelectromechanical systems. So there's a lot of history in this field. They're actually going to have a MEMS birthday party, I think at Stanford. One of the first companies, Lucas Nova Sensor, started 25 years ago. So they decided to celebrate the company's 25th year anniversary along with a MEMS birthday. And they're trying to figure out what people consider the first year that MEMS was actually a device, was a name that people used. They're also trying to figure out when did MEMS devices start being made and what people consider to be the start of MEMS. Most people say it's the late 50s or early 60s, in that range. And you'll see why in a few minutes when we go through this lecture. Just an FYI, this picture you see on the first page is that of a LIGA gear. LIGA is another type of micromachining technology that we haven't talked about yet, but it's lithography Galvo-Abformung. It's a German acronym. The Germans actually started this type of machining. It's to make very high aspect ratio parts. So that means tall and skinny parts. Okay? A lot of the pictures I've shown you and a lot of the applications that we've gone through, the parts are flat, right, and broad. Like semiconductor chips are very thin and broad. Those are low aspect ratio parts. Okay? LIGA is also referred to by the Sandians as long-involved German acronym. Okay, but it's a cool process. It's a cool technology, and we'll spend some time learning about that in a couple of weeks. Okay, so microelectromechanical systems started in a lot of different places and different ideas all across the world. And MEMS technology started to be evolving, and people needed a name for it, and they came up with the name MEMS. And I'll find some more about the origin of that term, microelectromechanical systems. Dr. Wood, one of the professors I work with at UNM, was actually at the conference, and he was one of the guys who came up with the name, him and 2 or 3 other guys. But I need to get the information on that, and then I can update that as well. MEMS applications started being developed probably, most people would say, early 60s. Okay? But this unit's going to give a broad look. You can study the history of MEMS, for a long time. There's a lot of detail in it, but we're just going to hit on some of the highlights. Okay, by the end of this unit, you should be able to name at least 3 MEMS technology processes. I'll give you a hint now. It's surface micromachining, bulk micromachining, and LIGA are 3 of the major ones. And then you should be able to remember at least 3 major milestones. And there's plenty to choose from, but try to remember at least 3 of them. So what are MEMS? Well, like we've been talking about in the last couple of weeks, we usually manufacture MEMS on semiconductor materials. Silicon is the biggest one. About 90–95% of the MEMS devices are made on silicon. The picture there is that of a blood pressure sensor made by Lucas Nova Sensor. So those guys are the ones that are going to have the birthday party for MEMS. There's 3 of them. 1, 2, 3. So you can see them arranged. Right? And that's a real head of a pin. And that's a real basic sensor, right? Nowadays, they can make them smaller. They can make sensor arrays. They can do all kinds of crazy stuff. That picture is probably 20 years old, I would venture to guess. Okay, so we make sensors. Sensors is a big deal in MEMS. Actuators is the other way, right? Sensor senses something. Actuators cause something to move. or it results in something. Types of products are accelerometers. We talked about that. We measure inertia with that, changes in inertia. Switches, light reflectors of different types. We call them spatial light modulators. They're used in automobiles, aerospace, biomed, inkjet print heads, wireless optical communications, and they range in size from about 1/1,000,000th of a meter or so to a millimeter. So when we talk about MEMS, some people put a size to it. They say, okay, anything about a micron or so big or bigger is MEMS. Other people say it's a microelectromechanical system. So it just depends who you talk to. There's still controversy on the definitions. So in 1947, the first transistor was made. That's pretty big. It's about 1 centimeter tall or so. William Shockley, John Bardeen, and Walter Brayton from Bell Labs made the first transistor. And they made it out of germanium. Germanium was a good semiconductor material that you could get pure pieces, and they actually made a transistor out of it. Later on, they found that silicon's a better material to use. It's easier to work with and a lot cheaper. But the first transistor was made out of germanium. And that's another type of semiconductor material. Okay, so if you look at the periodic table, it's in the column that you find silicon, right underneath it is germanium. So it has similar chemical properties as silicon. Okay? Yes, it has the same crystal structure. So if you go to that website, that crystal viewer, you can select germanium, and it's the same structure. The spacing of the atoms changes a little bit. Pardon me?
It's more rare.
Yeah, it's harder. It's harder to find. It's more expensive. So people like to use silicon. There's a lot of silicon on the planet. Just go to any beach, right? Silicon dioxide is what sand is. So silicon is. I can't remember the number, but it's a high percentage of our Earth's crust is silicon. So it's really convenient that we are blessed with having that much silicon around. So we're never going to run out. And of course, transistors are the basic building blocks of just about every gadget we use these days. Later in 1954, we discovered the piezoresistive effect, both in silicon and germanium. That was important because that led us to develop pressure sensors. Okay, so it was discovered in 54 by C.S. Smith. The piezoresistive effect of semiconductors can be several magnitudes larger than that of metals. Before that, we used strain gauges. Okay, we still use strain gauges made out of metal. If you stretch a piece of metal, it'll change its resistance. And you can put that in an electronic circuit and translate that change in resistance to a stress. So, a wire stretcher, yeah. Wire stretcher. Funny guy. They actually have strain gauges you can buy. I think they're made out of nichrome. And you can attach them. Civil engineers will put strain gauges on walls or across a crack in a building to try to monitor how things are moving over time. Yeah, you can use strain gauges to test all sorts of things. They typically will attach a strain gauge onto some material that they're interested in. And then they'll bend that material, and the strain gauge will tell them how much it bent. Now they use piezoresistive effect, which is based on the crystallography of the semiconductor. So if you apply pressure to a semiconductor, it will change its electrical properties, in this case the resistive properties of the semiconductor, and it can be much more sensitive. Okay, so the common pressure sensors built. MEMS pressure sensors are built based on piezoresistive effects in the semiconductors. And a real good website is one by Kulite, K-U-L-I-T-E. K-U-L-I-T-E. It's a company that started, I believe, in the 60s. And those guys make pressure sensors, MEMS pressure sensors. They've been doing it for a long time. And they use this basic property of silicon. Okay, let's see. I think we covered just about everything on this page. So we've got some pictures here. The upper right picture is the backside of a pressure sensor that we actually make as part of the next course. And the bottom is the front side of that same pressure sensor showing the piezoresistive material. Now metal's considered piezoresistive as well. Okay, but the effect is much smaller than it is in silicon. So we actually use a metal strain gauge to do the piezoresistive component of the pressure sensor. In 1958, the first integrated circuit was developed. Okay, that was done at Texas Instruments by Jack Kilby. I actually met Jack Kilby. He gave a presentation when I was a physics student that I got to go see. As part of the American Physics Society student chapter. Not a very dynamic guy. You know, he's kind of introverted. Today, no one would hire him. Okay? I don't mean to diss him. He's a brilliant man, but he's not, you know, he's very quiet. He doesn't, you know, say how great he is, right? Like Matt. Matt likes to say how great he is, but Jack Kilby is a very quiet individual, but very, very sharp. And the story is that, you know, his first few weeks at Texas Instruments started right before Christmas, and he didn't have any vacation built up yet. So everybody was off on vacation for like 2 weeks, and he couldn't take any vacation, so he worked in the lab all by himself, and he came up with the first integrated circuit. So we should take vacation away from everyone, and so they can invent things. But he built this solid circuit, he called it. It was consisting of 1 transistor, 3 resistors, and a capacitor. What's cool about that, before that, we made discrete devices. You could buy a transistor, you could buy a resistor, you could buy a capacitor, and you can wire them together and make a circuit. Right? That we knew how to make discrete devices. The transistor radios came out before '58, okay? And they were discrete parts. Well, Jack Kilby figured out how to make all of these parts in one shot. And what was cool about that is now you can make an integrated circuit, right? And now we have, you know, our iPods, iPhones, all of that stuff. Really complex systems that just blows away this picture of the first integrated circuit.
How big is that?
Oh, the picture. I'm thinking the picture. Yeah, the picture above the blow up is an actual integrated, the first integrated circuit between the 2 fingers.
So it's about like maybe not even an inch.
It's about the size of a regular computer chip now. So the chip hasn't really changed size. We just pack 1 billion of these things in there instead of 1. Okay? Fairchild Semiconductor made its first unitary circuit on a silicon chip. And then the patent was awarded to Robert Noyce. There was some contention about who invented it. One's an IC, integrated circuit. Another is something else. So, you know, at the time, people were trying to come up with ways to integrate electronics into smaller and smaller packages, because the person who could do that could make more money. Because electronics was starting to get into everything, right? Everybody had a TV, or we're starting to get TVs back then. Everybody had a radio. So if you could make electronics better, faster, and cheaper, you can take over the whole market. Yeah, those old companies like RCA, right? That made vacuum tubes. Right. So what Steve's saying is that you could replace boards easily. You didn't have to go to the component level.
Yeah.
That's another advantage. It's also a disadvantage because a board can be extraordinarily expensive depending how rare it is. If it's in your car, you might pay $1,000 for an electronic board for your car because Ford's the only one that makes it, right? Or provides it. So it can get expensive. Let's move along. In 1959, there's this guy called Feynman, Richard Feynman. He liked to play bongos. He wrote poetry, he wrote books. Supposedly an excellent, excellent physics lecturer. He went to Brazil and tried to teach physics down there at the university for a while. So he's quite a man. He's very diverse, very broad in his knowledge base. So he was able to bring in things from other disciplines and kind of put things together. So he didn't just focus on physics, but he learned as much as he could about other technologies. And he gave a speech back in 1959 for the American Physical Society. I think it was at Caltech is where the speech was given. And it's entitled, "There's Plenty of Room at the Bottom." And what he was saying is, you know, we can still go really, really small and do more and more things on the small side. So you're going to have an assignment where you'll read his paper and answer a few questions. It's kind of an exciting paper in my mind. I found it real enlightening. And it's, like I mentioned before class, it's probably one of the most referenced papers in the general public when it comes to MEMS type of technology. People mention this all the time. So he challenged his audience during that time to write something on a scale of 1/25,000. So, you know, can you shrink down typeset in the Encyclopedia Britannica by that amount? And actually write something on a surface and be able to read it. Right? You have to be able to see it too, right? Otherwise, how do you know? Now, of course, we've gotten much smaller than that. This challenge was actually met in the 80s by a graduate student. You can Google that and find it, and that's probably one of the questions on the assignment. And then the other one was making a very small motor. I think it had to fit within a 1/64 of an inch per side cube. Now the Forsyth Nanotech Institute gives out Feynman prizes every year in nanotechnology. So nanotechnology is the application of nanoscience to technology, actually making something using nanoscience. In 1968, this was a big deal. This is the resonant gate transistor developed by Harvey Nathanson and his group from Westinghouse. It was part of, I believe, an Air Force project. So this is a transistor, but the gate is actually floating. It's a cantilever. It floats above the source and drain. So as the gate gets closer to the source and drain, if you have a voltage on it, it'll turn on the transistor. As the gate gets further away, it'll turn it off. So by using a vibrational mode, the natural frequency of the cantilever, you can drive a signal through there. And it was made to filter certain types of high-frequency signals that the Air Force was interested in leveraging. And it's a wonderful device, and it's quite simple. So once you understand how transistors work and you learn a little bit about how cantilevers work, you can build one of these in the clean room as well. Okay? So it's about 1 millimeter long, which is huge by today's standards. Now most cantilevers are about 100 microns, which is 1/10 of a millimeter. Okay, it responded to a very narrow range of electrical input signals or frequencies, and that's what it was built for. But it was the first time someone demonstrated using surface micromachining methods to make a MEMS device, an actual mechanical device. They used the exact same processes that they used to make circuits, but now they made a moving part. So now you weren't just moving electrons, but you're also moving mechanical parts. So that's 1968. That wasn't too long ago. I was 6 years old. You guys probably weren't born yet, some of you. So, okay, Steve was 10 years old. I'm not going to ask Mario how old he was in 68. You were 18. All right. See, you grew up in the best time, Sputnik and all of that stuff.
Oh, yeah. That was a big scare.
That's fun. Oh, my. That was, with NASA taking off, that was the best time. Anyway, I digress. Let's stick to the topic at hand. In '71, we invented the microprocessor. So Intel took a lot of the technologies from TI and from Fairchild, and came up with a way of putting together integrated circuits to make a microprocessor, something that could think, right, or do logic. And they created the first calculator, or one of the first calculators. It's kind of a big calculator, but there was an Intel chip in that calculator on the right side. And it was the 4004 microprocessor, which is shown on the left side. And that started to pave the way for the personal computer. Okay, and Intel is still the big dog, right? So having a little IP or intellectual property goes a long way. In the 60s and 70s, we started developing all kinds of processes, right? And we've got some papers that are referenced there, electrically, chemically controlled thinning of silicon. So how do you etch silicon away? Anisotropically. And we talked about that in the crystallography unit. You know, a little bit about anisotropic etching. We leverage the crystallography of the silicon, noting that the 111 plane etches much, much slower than the 100 plane, so you can make different kinds of shapes. These guys worked on those basic processes back then and figured out some of the techniques we still use to this day. Now it's just a matter of refining it, making it cleaner, faster. But the basic chemistry was all figured out back then. Okay? Selective etching is real important, as well as bulk etching. So bulk etching, we kind of use that term lightly. Bulk etching means you remove a lot of material. So you're trying to drill a hole into the silicon, right? It's like taking a backhoe. You're moving a lot of material around. So we call that bulk etching. The idea there is imagine Mount Rushmore. You guys know what Mount Rushmore is? Okay, it started as a mountain. So the idea with bulk etching is similar to Mount Rushmore. You start with a mountain, you remove everything that doesn't look like a president. Okay? Bulk etching's like that. You start with a piece of silicon and you remove everything that doesn't look like an accelerometer. Okay, that's kind of the idea. Or it doesn't look like a channel for your microfluidics. Or it doesn't look like a hole through the wafer so you can do through the wafer electrical connections. Now that's bulk etching and bulk micromachining. Okay? That's the idea. You can make real thin diaphragm pressure sensors. Like we saw Nova sensors. They built the pressure sensors probably 20 years ago, maybe more, 30 years ago. It's considered one of the earliest commercial successes of microsystems. That's why we talk a lot about pressure sensors in this class. It has a historical relevance, and a lot of the basic processes are used to make them. So it's a good vehicle to learn all the different processes. Then in '79, Hewlett-Packard came up with the Inkjet nozzle. That was a big deal. You know, we could start printing stuff at home, right? Probably within 10 years from that time, people could start printing photographic quality things at home. And that's all because we learned how to make nozzles in silicon. How do you make a little nozzle, right? You can do anisotropic etching of crystal, silicon, and you can make very precise, repeatable nozzles. Okay, so the way the inkjet printhead works is if you put a resistor underneath some ink, you can put current through it, right? What happens if you put a current through a resistor? What happens to the resistor? It heats up, right? Well, if you make the resistance high enough by making the wire thin enough, you can get a heater, right? So now if I put a pulse of electricity through a very small heater, a micro heater, I can heat up that ink so it forms a bubble, right? The bubble rapidly expands because it's heating up. Well, that causes a pressure wave inside the ink. And if you make the chamber small enough and put your heating element in there, you can push a little bit of ink out the nozzle with that bubble. Then you let go of that voltage on the resistor. The current stops flowing. It cools down. The bubble collapses. You're ready for the next. So we put a little heat in there. We create a bubble. The bubble expands, forces a droplet out. That's the basic idea. Okay? So the inkjet printhead, that's how it works. And now they don't just use ink. They figured out they can take different kinds of DNA snippets and spray it onto a DNA lab on a chip. So if you fill those inkjet nozzle cavities up with different types of DNA, you can spray them onto a chip and identify specific things you're looking for, depending on what DNA snippets you use. So if the complementary part of that DNA snippet attaches itself to it, then you know you've found that piece that you're looking for. So that's another application for inkjet printheads. It's not just for ink anymore. Anything you want to precisely place that can be in liquid form on a surface, you can use an inkjet printhead. Okay, in '82 they invented LIGA in Germany. It stands for X-ray lithography. Galvo-Abformung, okay, LIGA. Translated loosely, it means lithography, electroplating, and molding. So this is a way of taking a pattern, making a very small mold, and using electroplating to make very, very small parts. You can also use it to make very small stamps. So you can stamp out a lot of parts from one LIGA part and go into high volume. And this was invented and developed in Germany. Sandia National Labs has come up with processes very, very similar to that out on the West Coast. You need a synchrotron radiation source. So the light bulb's the size of a couple of football fields, right? It's a synchrotron radiation source, and we'll talk more about that later. But you can use that X-radiation source. It's very collimated. The X-radiation travels relatively long distance in a straight line, so you can make very tall and skinny parts. Okay? That's the key. If you need to make a tall and skinny part, you might want to look at a LIGA process. They've changed the terminology a little bit over the last 2 or 3 years. They're stopping the use of the word LIGA, and they're calling it HARMST, H-A-R-M-S-T. So if you ever see somebody talk about high aspect ratio stuff, they may call it HARMST. HARMST stands for High Aspect Ratio Microsystems Technology. Okay? It's a little bit more descriptive than LIGA. LIGA stands for Long Involved German Acronym. Okay? People had a hard time with that. But high aspect ratio technologies are used for a lot of different things. They don't always use synchrotron radiation sources. There's other ways to make things that are high aspect ratio. So the people in the field decided to make a larger term for those type of processes. 1986, that wasn't too long ago. Most of you were probably born around by that time, right? 86 is, what, 24 years ago. Well, some of you weren't born yet. But 86, they invented the atomic force microscope. IBM did that. IBM is still inventing stuff. Those guys have a nice laboratory in the Northeast, up in the Albany area. T.J. Watson Center, I think they call it. It's one of the few big labs that are left, industry labs. So they invented this probe. They wanted to look at very, very small structures. And somebody came up with an idea of using a micro cantilever. And you could run it across the surface. And the cantilever goes up and down. Reflect the light off of the top of it. Watch how the light moves. And you get an idea what the surface looks like. It's a little more complex than that. But you get the idea. Pardon me? Oh, how does an SEM work? You use a very narrow electron beam. And electrons have a wavelength associated with it. So you can image very small things with an electron beam. Usually the way it works is the electron will hit the surface of the material and knock another electron off of it. That's called a secondary electron. And you can image that coming off the surface. And by rastering it, rastering the electron beam, you know when it hit and where it hit. So if you get a signal coming out, you know where that signal came from on the surface. So it's a way of synchronizing the electron beam motion with the detector, and you can build up an image on a black and white TV screen, okay, of what you're looking at. That's the basic idea of a scanning electron microscope. Okay, and they use different types of backscattering detectors to get different types of images from the same basic idea. With a atomic force microscope, you can get down to a lot smaller scale, usually on the order of a few nanometers or smaller, tens of angstroms, tenths of nanometers actually. And you can probe a surface, so you can see individual atoms to some degree. Okay, it's a representation of what the surface looks like, but you can see crystal arrays. You can Google it. You can look at atomic force microscope images, and they'll show you what the 111 looks like and the 100 looks like by actual measurements using an atomic force microscope. And you'll see the crystal, the arrangement of the atoms is different depending on what plane you're looking at. So. Yeah, you can use, this is called a profilometer, right, on a bigger scale. How many of you know what a record is? Yeah. A vinyl record, right? That's a stylus. It goes up and down in the grooves, right? And also left to right. And you can measure the amount of motion left and right and up and down. They usually use electromechanical transducers to pick it up. It's the same idea. You just shrink it down smaller and smaller and make it more sensitive. They actually look at the current that comes out of the tip. If you keep the tip a certain height above the surface, you'll get a certain current coming out of it. And by keeping the current constant, you know the height's constant. So they'll move the tip up and down for constant current. And then by the amount they move the tip up and down, they know what the surface looks like. So. Right. Right, the dictaphone and the phonograph, they were basically the same thing. One went one way, the other went the other way. If you talked loudly into a cone, it would funnel the sound down to a very small diaphragm, which would push a needle up and down. While you're rotating a disc, and the disc was on one of those worm gears, right? Or the stylus was on a worm gear, then it would slowly move towards the center or away from the center, and you'd make your own phonograph. You used to be able to go into studios and press your own phonograph. So that kind of used the idea of a stylus. And actually, the IBM folks ended up taking that atomic force microscope concept, and instead of reading surfaces, they developed a way of writing the surfaces with the same type of stylus. So now they can make devices that record information on a very small scale. All right, let's move to the 80s. Right? We had our first rotary electrostatic side drive motors at University of Berkeley. That's on the bottom left there. So you can see these different leads coming in. You apply voltages to it. The wheel on the inside is probably grounded, so you can make a stator. And by changing the voltages on these leads coming in a certain way, you can drive a voltage around in a circle, causing that rotary part that looks kind of like a gear or a fan blade. You can get that to spin. So that was a proof of concept idea, and it actually did function. On the right side is a lateral comb drive. Okay, and the way that works is you have two interdigitated combs, kind of like the comb you use to comb your hair. If you take two of them, put them together, you apply a voltage to one and ground the other, you can get them to attract each other. You get one set of combs attracting to the other, but the moving comb is on a spring, and that spring will bring the comb back to its original position once you release the voltage. So you can get things moving, you know, back and forth in terms of the lateral comb drive, and you can make things go round and round with the rotary drive. I haven't seen a successful application of the rotary drive. I don't think it works to drive anything of any mass, so the comb drives are much better, and you can convert that to a rotational motion. In '92, Silicon Light Machines developed the grating light valve, also called the grating light modulator. So if you learn about gratings, gratings are formed by having reflective elements spaced equally, and it'll cause light to bend in a certain way. It actually, it'll diffract. And if you can change that grating by moving the reflective surfaces up and down, you can actually modulate light. So we'll have a little bit more on that later, but that was a really interesting device, and it's actually functional, and I believe Sony owns the license or has a license for it. And they produce large, very, very large display units used for flight simulators. But they're expensive to make, they're hard to make, so they haven't come into the consumer market yet. Okay, the DMD is different. You use an array of mirrors, and you actually reflect the pixels to a lens. This diffracts it. It doesn't reflect it. It's a different principle. And what's nice about this, you can change the intensity by the amount of how far you pull down these alternating bridges or structures. So you don't have to flip it on and off more times or less times per second to get differences in intensity. You can actually get a gradient of intensity by just making it more or less of a grating. So if you learn a little bit about gratings, then think about, okay, if I put all of these bridges up, right? If I don't pull them down, if they're all up, it's a mirror. If I pull every other one of them down a quarter of a wavelength, it'll diffract the light completely. And if it's anywhere in between a quarter of a wavelength and being full up, You can adjust the amount that's diffracted. Okay? So there are other optoelectrical mechanical systems. We like the term MEMS. One is the DMD you mentioned. That's another MEMS device. And there's another one by Microvision, which has one mirror, and they do a raster scanning approach to draw images up on the screen. So
now, does this have, there's a race to find a faster computer, one that usually uses light instead of printed circuit boards that wouldn't have to access memory so much. I guess the problem is the mechanical connection between light and the circuits. Is this something that would be used in that application?
well, that's a good question. They do use and want to use mirror devices to do switching. So if you're sending data down a fiber optic and you want to switch it from one part of the computer to another or from one place to another, you can use mechanical mirrors to do that. Then you don't have to convert the signal to an electrical signal, send it down copper, you know, do your switching, and then create an optical signal again and put it back into a fiber optic cable. You can bypass all that by just having go from one fiber optic cable to another using a mirror. Okay? So there was a big boon on that in 2003. There were lots of MEMS companies that came out to make optical switches. The problem with that is the dot-coms went belly up about the same time. So, you know, everybody wanted fiber optic switching, high bandwidth and all of that back in the early 2000s. And so optical systems were a big deal. But after the dot-com bust, a lot of these small MEMS companies went out of business because there was no venture capital anymore. Nobody wanted to invest in it because all the dot-coms lost all their money. They were the guys investing in it. Okay. Well, we went a little off task, but that's all right. So there's a lot of different display technologies that use MEMS devices. Back in '93, the Microelectronics Center of North Carolina created MUMPS. That's not a disease. Okay? It's multi-user micro... Where is it? Multi-user MEMS process?
Yeah, I guess so. That would be MUMPS.
It's defined in the reading. I always forget what MUMPS stands for, but I know it's multi-user. And the idea there is they came up with a process so lots of different people can design using that process and be able to create devices. So some examples are given at the bottom. You can see a very basic chain type structure, and then a basic, I don't know what that is, a gripper. Okay, so you can grab things with it. And then on the right side is a similar process called Summit 5. That's one that Sandia National Labs developed, which is quite similar to the MUMPS process. Okay, and we will be designing using the Summit 5 process. In 1993, we made the first accelerometer. Analog devices were the first ones to really make a whole bunch of them, right? High volume, cheap. Once it gets to the point of being cost effective, then everybody wants to buy it. So they saved a factor of 4 going from the TRW macro sensors down to the analog devices accelerometer. And that was based on surface micromachining technology. Very similar technology used to make computer chips. In '94, we invented the deep reactive ion etching process. Bosch actually did that. They're a company in Germany. You might know them for their spark plugs. But they make lots of car parts and big on sensors. So their sensor technologies are top-notch. I think a lot of the sensors in your cars these days are made in Germany by Bosch. So they invented this process, and the idea was they wanted to etch into silicon very deep, very straight. This process was actually licensed by the DRAM manufacturers, right? The guys who make the chips in your computer that have lots of memory. The way you hold memory is you hold charge on a capacitor. If you make your capacitors flat, you know, horizontal, you can't hold much information, or you can't make many capacitors. If you make them vertical, you can stack them up and get more density. So by making vertical capacitors, vertical structures, you can actually do much better. And then, you know, Lucent Technologies came out with optical networking switches. Lucent, of course, is the baby research organization from Bell Labs. Okay, so they were interested in optical networking. Okay, so switches and optics are a big deal. Bio-MEMS are more recent, and you're seeing them everywhere. And this is a really big industry. So DNA arrays, lab on a chip. Healthcare organizations want to keep charging us a lot of money, but make the tests cheaper for them, right? Okay, so they don't want to, they can't keep raising costs forever. Yeah, they just they keep their profit margin high. But it's okay, because if you can go into a doctor's office and get checked for something right away, then that's a good thing. Get a shot instead of getting cut open, right? Yeah, doctors don't know how to ask patients questions and figure out what's wrong. They need a gadget, right? So get into the Bio-MEMS business. You'll make a lot of money. Yeah, just eat these sensors, and well, they have the pill cam. They actually have a pill or a camera inside of a pill you swallow, and it takes pictures that goes through your GI tract. It's a lot better than a colonoscopy, right? I just don't want to have to be the guy who retrieves it. Yeah, you can implant any kind of device that you can think of in your body. No one's going to force you to get tracked, right? So if that would be up to you if you wanted GPS on board all the time, even when you're naked running in the desert, right? You know where you are. Anyway, we digress. Let me get this last slide done, then you guys can go home. Okay, so we're creating a lot of MEMS devices to sense things. We're creating MEMS devices that help us in safety aspects, like the airbag sensors. We're creating devices that we can put in the body to monitor different things. And the MEMS devices are getting smaller, and nanotechnology is enabling a lot of this technology. So we've come up with yet another term called NEMS, which is nano electromechanical systems. So if you add a little nano to a MEMS device, you can call it NEMS. Okay? So you can keep thinking of different applications. The sky's the limit. The key thing is that we have now a lot of building blocks to work with. We have a lot of different Legos to build MEMS devices out of. Different processes, different materials, all of that. Okay? We're out of time, so we'll start with major MEMS milestones next time. It's probably only a few slides. It's in your reading, so please start the learning module and do all the reading. This is all listed in there as well. And it kind of lays it all out in front of you so you can kind of see how the history flows. All right.